All right. Greetings. How does it feel to be in your second to last biostatistics lecture or of the semester? Bittersweet, I hope. All right. Good. Good. We don't want to frighten you off in your first semester. We wait until the subsequent semesters when you decide it's too late to change your minds. All right. So we're going to cover analysis of two continuous variables today with simple linear regression and correlation, covered in chapter 7 of your textbook. Oh, and actually, I should have updated this. I took this non-parametric part out. I'll put that in next week. So it's just these first three things. Hello. Good to see you here. And I have you showing on screen today, so I won't miss if you ask any questions. Oh, is there audio? There should be. Yeah, I see the lights coming on. So if you do not see audio, it's probably because you're muted, because as far as I can see, it's being picked up here. Okay. Okay. Okay, good. Everything is working online. So what we've been covering so far this semester has been, we had a bit on descriptive statistics, which is really about looking at individual variables and just describing them through some numeric summaries or plots, and then a while on inference, confidence intervals, hypothesis testing, which was about the association between two variables. We're getting into now regression, and we'll do some more on regression next class too. But in regression, we actually have we will think about the problem in terms of a response variable and predictor, just one predictor variable today, and multiple predictor variables when you get into multiple regression. But this is it's a bit of a different context in that it's not just an association between two variables. In regression, we're using one or several variables to predict the other variables. When we plot these, the predictor is on the x-axis, the response is on the y-axis. We can predict things about the response variables, and we can also infer things about the coefficients of the x variables. So just to summarize some of the stuff we did already last week, the categorical variables, that was for two categorical variables, so race and the death penalty. Let's see. Is the screen doing weird things? That has been known to happen with this in presenter mode. I'm going to try something different. Let me know if it's better. I might just have to do it like this, which is annoying, but it seems to be a drawback of Hangouts on Air. Okay, so this was about association between two variables, but we were talking about strength of association and about independence versus dependence. For one categorical variable and one continuous variable, we covered the t-test and analysis of variance with some plots like this and those methods. So we're talking now about two continuous variables, and the method of inference we're going to use is regression analysis, and the descriptive visualization is the scatter plot. So the scatter plot provides you with a lot of detail. It shows you every data point. And it's a useful thing to look at. It will show you things like whether the relationship appears to be linear, how strong it tends to be, but it's a lot of detail. The correlation is going to be a single number summary of how strong that linear association is between the two variables. So even though we're talking about response and predictors, there's not necessarily, it does not have to mean that there is a causal effect between them. We have to choose one as the predictor variable to put on the x-axis to use as the x in the equations I'm going to show, but it's not necessarily causal. Here are a couple examples of linear relationships. This is a positive linear relationship with some noise in addition to the linear relationship. Here's a negative correlation in a linear relationship with a little bit less noise, and a couple examples of nonlinear relationships. In this case, the linear component would likely be pretty close to no association at all. In this case, there would be some linear association in addition to the nonlinear association. So strong relationships are where you can explain most of the variability in y just by variability in x. There's only a little bit of variability left over that is unexplained by your predictor variable. And weaker relationships are where there's a lot of variability left over that you can't explain by your predictor variables. Here are a couple examples of no relationship. So this is kind of x and y have the same variance, but there's knowing about x doesn't give you any improved ability to guess what y will be. And that's the same case here. It's just here y has a lower variability than x. It's the only difference between these two. So as a concrete example, this is something where you have two continuous variables looking across a bunch of different countries, the percentage of individuals who are immunized for diphtheria, polio, and tetanus, and the under 5 mortality rate, which would be in individuals per 100,000. And we can see here an approximate negative association between these, although clearly it's not there is variability that's not explained by this. But so these are two continuous variables, and this is telling us that the more there's a relationship between with more percentage of individuals immunized, there's a lower mortality rate. So it's also a good example of where there may be some causal effect there. Some of these under 5 mortalities might be being saved by the immunization, and others of it might not be causal. So some of the variability from this line might be caused by other sources of variability, and also some of the relationship might just be non-causal as well, that other aspects of public health might be related to the immunization rate, and that also affect under 5 mortality. Any questions so far? These two lines shown on here, one is the mean of y, so this is just the mean across all of the values, and it's down fairly low because we have a lot of measurements down here, so it's not centered on the range of y. And this best fit line here can be interpreted as the mean of the predicted mean value of mortality for any given percentage of immunization. So the best fit line tells us that that expected mean varies with the immunization rate. So the difference between these two lines tells you something about the strength of the linear, well, it tells you something about the existence of a linear relationship, and it tells you something about whether this regression line helps you to explain under 5 mortality. And I'll show you this in some equations later, but in short, if the squared distances of these points, the data points from this regression line, are significantly less than the squared differences than they are from the dashed line, then that's a case where we're going to reject the null hypothesis, because this regression line is giving us additional information that helps us to predict the response variable. So correlation coefficient, you can even write in Pearson correlation coefficient. It is the Pearson correlation coefficient, sometimes also just called the correlation coefficient, is a measure both of the strength of this relationship and the direction of it. In keeping with the customs we've been using so far, we're using Greek letters for population parameters and Roman letters for sample statistics. So in the population, the association between two continuous variables can be described with the the population coefficient rho, and if we estimate it from a sample, we'll call it R, which is, by the way, also called the product moment correlation coefficient. It has lots of names. Here's how you calculate it. Let's look at the one for R here and look at what this is. So the X bar, that's just the average of all of the X values. Y bar is the average of all the Y values. So for each data point, we're just looking at this is the residuals of the X's divided by the standard deviation of the X's times the residual of the Y's divided by the standard deviation of the Y's. And then divided by the number of degrees of freedom. This looks very similar to this would be some of this on its own, X minus X bar, if this was just for one variable, this would be X minus X bar squared. Let's ignore this part for now. Over N minus 1, that would be the variance, right? And then this would be the standard deviation times the standard deviation. So if X and Y are the same, what are we going to get from this formula?
Okay.
you're going to get 1.
Which is a perfect correlation.
Yep. So a variable has perfect correlation with itself, a correlation of 1. Let's see, I need to make this a little smaller. So here's what a few of them look like. And this is a really common descriptor of data. It's like one number that's given to describe the association between two variables. So it's obviously not nearly as much information as you get from a scatter plot, but you don't need to plot anything. You can just give the number and it tells people something about the linear relation between two variables. So here are just some examples. Correlation coefficient of -1, it means there's a negative association and it's a perfect association. So knowing X is all you need to know Y. A somewhat weaker negative correlation, no correlation, a positive, somewhat weak correlation, and a perfect positive correlation. I'm going to show you in a little bit that these correlations have an equivalence to the slope of the regression as well.
Yeah, a question there.
Oh, there's a question.
Looks like on the graph. Second question.
Can you point out in the graph what a residual is? Oh, sure. So here the residuals are all 0. In the ones where it's not all 0, the residuals, residuals are with respect to a model. So this line represents a linear regression model, and the residuals are your observations minus your predicted values. And I think I have a plot of this later, but here it would be this value of Y minus this value of Y. It's the vertical distance.
So
Yeah.
each point would have like a different residual.
Yeah, each point will have its own residual. And keep in mind, it's not just the distance from this line, like perpendicular to the line or something, it's the vertical distance. It's, pardon? It's the same X value, right? So it's Y sub I, the value of Y that's observed, minus Y hat, or predicted Y for that value of X. That's the residual. Good question.
So what was the equation?
What's that?
Is there another question?
Is there another question? So is that equation for the line? What equation?
And then she thinks that she wants to raise the equation for line, but that's just a Pearson correlation.
Oh, yeah. So Pearson correlation, I guess you're talking about this. This is like a statistic describing a linear association between two variables. It is very closely linked to the regression, and I'll show you how it's linked to the regression. But it is different than a regression coefficient in that the regression coefficient, if you switched your X and Y, it would change, whereas R would stay the same. As you can see here, if you switch X and Y, you change the order of these two terms, and R stays exactly the same. So it's an association between, a measure of association between X and Y that is not a regression. So it's not the regression slope directly. Okay. So it's not that line that you see, it's just closely related to it. What's that?
It's the equation for the R value.
This is the equation for the R value, right? Which is independent of which is your X and which is your Y. It doesn't matter which is which is your response, which is your predictor. I will show you in a minute what its equivalence with the regression coefficient is. One difference between R and a regression coefficient is that it's unit-free. It goes between -1 and 1 inclusive, but it has no units. So even if your X and your Y have units of centimeters and pounds or something, it doesn't matter. There's no units to X. And -1 is perfect negative relationship, +1 is a perfect positive relationship, and 0 is no linear relationship. So unless that correlation is exactly plus or minus 1, it does not necessarily imply a linear relationship. I showed an example before where you saw kind of a curved relationship where you could have a high correlation even though there's a nonlinear relationship between the two variables. If it's 1, then it's linear and nothing else. But even if it's 0.9 or something, you could have a clear curvilinear relationship. It does not imply causality. That you can only know from the design of the experiment or other sources of knowledge about causality. And it can be sensitive to outliers. Yes?
So the interpretation is always like, according to this data, in our data, X variable has a strong positive correlation with this variable, with that variable. If that's what you forget.
Yeah, these you can say we observe these variables, DPT, vaccination, and childhood mortality are negatively correlated. You can say correlated, you can say associated. You could only say are causally related based on if it were an RCT, or you know from theory that they must be causally related. Yes.
So if the data was like exponential or like just like that curved shape, would you still use the R? Isn't that kind of like misleading?
So
Is
if
that necessarily something you would use?
yeah, so if your data are curved, exponential, or the relationship between them, R would give you an incomplete picture of their association. It would still tell you the strength of the linear component of the relationship, but it wouldn't tell you anything about the additional nonlinear relationship. So you can usually, an example like this bottom.
Like a dose response curve.
What does a dose response curve look like?
Like we were working with those a little bit in Viro the other day, that like if you give somebody aspirin, you get a positive effect for a little while, and then you start to get a negative effect.
Right. So it looks something.
It looks like that.
It looks like this.
It's good, and then suddenly you overdose on that.
Right. So in that case, R would be misleading. It would tell you there's no association if it looked like this, which is not the case.
Is there a statistic you would use in that case?
There are other statistics that you can use. The main options, you can do a multiple regression or a regression that actually fits this relationship. So this could be a quadratic relationship. If you fit an intercept plus a linear term plus a quadratic term, then your quadratic term would capture this relationship, and you would get an overall, what I'll show you is a coefficient of determination that would tell you how much of the variability of Y is predicted by X according to this nonlinear relationship that you fit. There are other things which you probably won't learn about at any point in your MPH unless I get a chance to teach another course or something, but generalized statistics to capture nonlinear associations. There is something called mutual information that that involves breaking this up into bins and saying, does, like, breaking this entire area up into bins and looking at it in a completely model-free way and saying, does the proximity of like the clustering of these into boxes, like if we were to put in even 16 boxes here, how many boxes contain all of the data points, is kind of an idea of what mutual information would be, which would be like, how much does some information of X tell you about Y? Well, if these are all contained only within 6 out of 16 boxes, then it tells you something, because there are a lot of, if you know it's in this box and you know it's in one of only 2 Y boxes, you know, then that it's also a measure that's between -1 and 1, but makes no assumptions about linearity. The thing you will learn about is multiple regression and using polynomials to fit. But yeah, if the relationship is non-linear, in a case like this, it's not totally horrible to use R to say, okay, maybe there's a correlation of 0.8 or something here, but your actual strength of association is stronger than that. It's just that you're not capturing the nonlinear component. So it's a bit of a misleading statistic then. You can do hypothesis tests on correlation. So like you're familiar with now, the hypothesis test is on the population parameter. So the null hypothesis of no correlation would be rho equal to 0, with alternative hypothesis being rho not equal to 0. And it turns out handily that if your null hypothesis is true, then as you take multiple random samples under some assumptions that I'll list later, then your this particular statistic, so it's you calculate the R, oh, I see there's another question, calculate R, multiply by this stuff, it turns out to be T distributed. So you can calculate a value of T and look it up on your table of the T distribution and decide whether or not to reject your null hypothesis. So this is a continuation of the t-tests, of the ANOVA, of the chi-squared test, where you calculate some test statistic where you know what its distribution is if your null hypothesis is true, and then you calculate the probability of observing the value that you saw or something more extreme. It's neat how that T statistic just comes up over and over again, isn't it? I'm still amazed by it, how many different things you can use it for. Turns out you can use it in multiple regression too. Like when you have multiple predictor variables, you can do a t-test for each one of those variables, not just for simple linear regression. It's amazing.
And then how would that read out though? If you do it for multiple, is it like positive all the t-scores?
No, it would just be for each variable. Yeah, so you could do, you know, if you had 2 predictors, you get a t-statistic for each of the variables, and you could decide whether they independently are associated with the outcome or the response. So just there's a question. Could you split up your data at the point it changes slopes and make inference using regression on just that part of the data sets? Not really, because, well, I don't know, tricky question. One problem is that you're visually picking out a subset of your data where your alternative hypothesis looks more true and then doing inference on it. So you're picking out like a section where the association looks more linear and doing your test for linearity on it. So potentially your visual inspection of your data set is going to bias your results, right? In general, you could do something like that. You can subset your data and do different things on different subsets of your data. But it has to be pretty carefully justified. I should have brought a glass of water today. So I'm going to say just use care, and in general, you can't look at your data set at hand and then split it apart in a way that matches your model better. Oh, really? Thank you. Oh, that's much better. So let me know if that answers your question. Screen went green, I don't know. Bad science, yeah. Okay, I'll leave that in there. So yeah, the point there is that you have to remember that your sample from the population is usually all you have. So if you use that to start forming new hypotheses, there's a possibility of bias. Ordinarily, you want to have your hypotheses formulated not just on the basis of your sample. It's okay to do some things to try to find a model that fits your population using your sample, but you have to be somewhat conservative and limit yourself in the amount of things that you do in that sense, lest you risk biasing your hypothesis testing. Okay. So the correlation coefficient is a measure of strength of association, like the chi-squared statistic, and more similar to things we've been doing. Regression is really something new, and it is a field that is not all of statistics, but it's a lot of it. The course that many of you will take from me next fall is almost entirely regression analysis. And regression analysis is all about predicting the value of your response variable from your independent variables, and about making inference on which of your independent variables are associated to your response variable, where the dependent variable or the response variable is the one we want to explain, and the independent variables are the ones that we use to explain it. In this course, we'll look at simple linear regression. There's just one independent variable and one dependent variable. And we can describe that as three components. There's the slope, there's the intercept, and then there's the random error, which is whatever we can't explain with the slope and intercept. I'm going to use capital X and Y to describe random variables and lowercase x and y with subscripts for the individual observations. Yes?
Why would we attribute it to random error rather than like other things in the environment or other factors or?
Yeah, so why would we attribute what is left over to, where did I write that? Yeah, random error as opposed to other factors. If we've measured those other factors, then we can try to attribute it to them. If we haven't, then we have no way to predict on the basis of them. So the random error is the component that we cannot explain based on our measured variables. It could very well be that there is another variable that we did not observe that would explain that variability. But in terms of what we have at hand and the ways that we can model it, random error is everything that we can't explain. So in some cases, it truly is random error, like measurement error, like, well, who knows, maybe everything has an explanation, but from the statistician's perspective, it's the things you can't explain. So here's your first regression equation. So this is the population level model. So I'm writing the capital X and the capital Y, and it contains those components that I mentioned on the last screen. So the dependent variable, it's the intercept plus the slope times the dependent variable plus the random error component. There actually is a case where the random error might be reduced without measuring those other variables that might explain it, and that is by different terms with the x outside of simple linear regression. For example, in that case where there's obviously a quadratic term or a squared term for x, that could change the residual errors. But no matter what model we choose, unless it's heavily overfitted to the data, there will always be a random error term. So in real life with measured observed data, there is always error. Yeah, a couple other ways that you might see this written. This is kind of an interesting terminology here that is used sometimes. This is, you could read this as the predicted mean value of y given x. So and you notice this one doesn't have an error term because it's talking about the predicted mean value. So this part of the component, the regression equation only, is predicting for a bunch of y values for a given value of x, this is the mean y value, and then individual y values will have this random error term added. But the mean of this random error term is 0. For the sample, this is one way to write the regression equation. That is that the estimated or the predicted or the mean value of y for a given value of x is this slope using Roman letters plus the intercept times the, oh, there should be a subscript I by the x here. And I'll put it in right now while I'm remembering. I. There. All right, here's your graphical picture of what the residuals is. So actually, I'm going to add to this that this could also be written in terms of the individual yi. So if this, instead of being this predicted value, if this were yi equals b0 plus b1 x1, then we would have the error term or the residual term as well, the e sub I added on to it. And those error terms look like this. So as I mentioned, they're the vertical distance of each data point from your regression line. The typical approach for fitting linear regression or polynomial regression, whatever, is to find the line that minimizes the sum of squares. So each of these differences, these residuals, you take the squares, you add them together, and then you adjust this line so that that sum of the squares is as small as possible. That's what your software is going to do when you fit a linear regression. It turns out that for simple linear regression, it can be solved exactly. You don't have to do it iteratively. But for more complicated regressions, it does have to be done iteratively. And the software will literally just try a bunch of slopes and intercepts for the more complicated cases, and then just return to you the one that gave the smallest sum of squares of the residuals. These, so I mentioned one reason to do regression is to predict y from x, and the other one is to interpret the associations between x and y. And a big advantage of linear regression is that the coefficients are highly interpretable. So this b0, the slope, that's the average value of y when x is 0, which may or may not be a useful thing to report on. B1, this is the thing that much of epidemiological analysis is about. It's about this, the coefficients between your predictors and your response, which in the case of linear regression is how much y changes for a given unit change of x. So if x is, what was the example we had? Immunization rates, then in that case, beta 1 would be, okay, for a change in one immunization per 100,000, how much does the mortality rate per 100,000 change? So very interpretable coefficients. Turns out that different types of regression models, they'll have different interpretations of these, which you'll get to, but it's a common feature of regression for the sake of inference that this is the key thing that we're interested in. As a side note, and a lot of my research is actually more about the prediction ends, and I will use models where you don't get any coefficients that are particularly interpretable, but you get better predictions of y. And there is often a bit of a trade-off there between an interpretable model and a model that predicts well. Not always, but sometimes.
I can imagine it's hard to explain to somebody how this predicts this, you know, like somebody who doesn't know statistics or does it. Trying to explain to them, like, well, so I ran the statistical test and it will predict, you know, like,
yeah,
confidently.
Well, although in some ways it's easier to say this predicts this than to say this predicts this, but it's not causing it. Yeah, And then you can have models where your coefficients have no meaning whatsoever. There, you have a black box equation for predicting y from x. Let's see. For regression, so you remember for analysis of variance, we broke up the total variance into the within group variance and the between group variance. And the total variance was the sum of the within group variance and the between group variance. This is basically the same thing. We're talking about a sum of squares, which is directly related to variance. And that total sum of squares of the residuals, that's what this is, it can be broken up into these two terms, the sum of squares of the errors. Does this equation make sense? Someone wanna, I'd like to hear someone else tell me about this. This is, I just wanna make sure that these three things, total sum of squares of errors, and the sum of squares of regression are very clear. So this is the total residuals. Or sorry, these are not the residuals. Y bar is the mean of y. So this is just taking each individual y and subtracting the mean of y. So if you didn't know anything about x, your best guess for y would be y bar, the mean. So you remember on that earlier regression line, we had one sloped line that was solid, and we had a horizontal line that was dashed. This y bar is that dashed horizontal line. So that's the total amount, the sum of squares of how much the observations y deviate from their mean. This component, the sum of squares of errors, these are the residuals. These are the things that, this is the term that we minimize when we do regression. So instead of just the mean of y, it's the mean of y given x. It's the distance of the data points y from our regression line. And then this final term is the difference between the y value of the regression line, or the predicted y, from the overall mean. So this is how different our regression line is from that horizontal mean line. Yes, question?
I don't understand why they use a square but not use the absolute value. So what's the point of using square?
Why do we use squares instead of absolute values? It's a good question. I can say that the behavior of the squares is better than the behavior of absolute values. Like that the result that you can calculate exactly the regression equation for the sum of squares doesn't exist for the absolute values. The mathematics behind doing regression works much better for squares.
The reason I'm asking is every time when I'm thinking about square, I just feel like it's gonna increase exponentially, something like that.
No, it increases quadratically with the square. Quadratic meaning to the power of 2.
But not
Right, not exponential. The important thing I can tell you about using squares that is nice is that if you plot this function, then when you get to the 0 point, it's smooth. It looks like a parabola, right? Whereas with absolute values, you have a discontinuity at 0. So the derivative is undefined. And anytime you have discontinuities in function, they become very hard to work with mathematically.
Right, so like if you were to graph it without the squares, it comes up as like a bunch of different points. But like the squares kind of like smooth out your, like when you plot it, you square it, it usually looks a lot cleaner. It might not be directly related to this, but whenever you have like a bunch of numbers or residuals or whatever it is, squaring them makes it actually visual. Like you can actually visualize it on a plot as opposed to just plotting it without getting the squares.
Yeah.
I don't know why.
I mean, using squares is also related to the variance and standard deviation, which when you have normally distributed data have nice interpretations. They enable things like the empirical rule. They are a part of the normal distribution. So like if you write out the equation for the normal distribution, it contains the standard deviation or the variance. So yeah, I think I can say it turns out being more interpretable and mathematically more consistent. Was there another question here? No. Okay. So we're breaking up our sums. Yes.
SSE is the distance of residuals from the line.
SSE?
Oh, good question.
Oh, okay. It looks like I need to clear questions to make sure. Can't tell how it decides what order to show them in. So SSE is the distance of residuals from the line, sum of squares of error. That's right. SSE is yi is the data point and y hat is the line. So it's the SSE is the sum of squares of the residuals from the line.
Shouldn't that be y hat sub I? It's dependent on x.
Yes. Yep. Good point. This should be y hat sub I because it's dependent on x. I'll put that in too. There. Thank you. Okay. So when you break up your regression that way, and that, by the way, is very general, that this way of breaking up your errors is not limited to simple linear regression. You can do this for all kinds of regression. Oh, okay. Yeah, there's a 30 seconds to a minute delay here. It's a general way of splitting up the variability of y into what we can explain and to what we can't explain. And the ratio of those two things, so the sum of squares of the regression divided by the total sum of squares is what we call the coefficient of determination, or R squared. It varies between 0 and 1. It's always positive. And you can think of it as the fraction of the variability in y that you can explain with x, because sum of squares total is the total variability in y from the mean, and the sum of squares of the regression line is the amount of it that you're explaining with your regression line. So this is a measure of the quality of your predictions of y from x, not of the direction of the association. Turns out that it's closely related to the small r that we saw before, and in the way that you would hope. Turns out that big R squared is the square of the Pearson correlation, or the Pearson product moment. It's nice, huh? So little r told us about the association between two variables and the sign of it. Big R squared tells us about the quality of our predictions of y from x, and they're closely related. It's just R squared doesn't tell you anything about the sign of the association, because it's always positive. It just tells you how much of the variability of y is explained by x. So unlike with R, this was correlation of -1 and a correlation of +1. These are both R squared of 1, meaning 100% of the variability of y is explained by a variation in x. A couple examples of R squared somewhere between 0 and 1. It's not 0 because we're explaining some of the variability of y with x, but it's not 1 either. You notice that this this strength, or the magnitude of R squared, has to do with both the spread of these points from the regression line, and with the slope of the regression line. Because if this were a very large slope, then we're explaining a lot. We're explaining more of the variability of y with x. What do you think would happen if we had one extreme outlier point here? Like, say this point, instead of being right here, was down at -1,000,000. What would happen to R squared?
There would be less of a correlation.
No. No, so you have a bunch of points that are all around here, and then you have one point that is way, way
It's an outlier.
down here. It's an outlier. And what's its effect on R squared going to be?
Since it's squared, I don't think it does.
It's going to affect the regression line a lot. This regression line is going to get pulled down because the square of that residual is going to be huge. So it's, when you try to minimize it, it's going to have an outsized effect on your slope. It'll pull the regression line way down here. And when you don't use x to explain y, you'll have a mean that's, somewhere around here. You'll have really huge residuals from your zero slope line, or just the mean of y. And adding that slope will reduce those residuals a lot, because it can reach most of the way down here to this outlier. So you can have 100 points around here with no correlation, or a 0 R squared, and one point way out here and end up with an R squared pretty close to 1. That's the effect an outlier can have. So outliers are important when it comes to linear regression.
So what do you do to the outlier if that was the case? You just not include it? Or?
It's a good question. What do you do with an outlier? Do you just not include it? You have to be careful about not including any of your data, because it might just be, it might be a real value, and it might be that there's something wrong in your model. There's something you don't understand. Or it might be an error in recording. It might be that you know, someone recorded a missing value as 999 and you didn't catch up on that when you did your data cleaning. So you need to look into it. But in general, you need to be careful about justifying removal of outliers, because it has a large effect on your analysis, and it's a way of making the data fit your model better. So you're, you know, when you're doing a linear regression, you're assuming some model for your data, and you're starting to make the data fit your model by selectively removing components of it. So you need to be careful, and you need to try to carefully justify removal of any outliers. There are also then probably a better option if you have extreme outliers and you can't justify removing them, but your model's obviously wrong, is to go to a different model. So you're changing your model, not your data. You can go to non-parametric models that I'll just summarize for you next class, which are not sensitive to outliers. There are also robust forms of regression that just reduce the influence of outliers. Here's an example of an R squared of 0. So the sum of squares of the regression from the mean line is 0. So R squared is 0. Of course, in real life, you would never get an R squared of exactly 0, just fitting, even if you're fitting to a relationship that doesn't exist, it will give you some increase in R squared, and that's where hypothesis tests come in to tell you whether that deviation from no association is more than you expect by chance. Like all of the methods we've learned, there are some assumptions involved. This is a new one, linearity. So by the form of the regression equation, we're making an assumption about the association, that the relationship between X and Y in the population is linear, and that the true regression line is straight. Here is one that we didn't always make in the t-test, but we might have. Remember, there was an equal variance and an unequal variance version. We have to make the assumption of equal variance here. It's called homoscedasticity, and that is that the variability of Y doesn't depend on X. So whether we're looking at small x or large x, the variability of Y about that regression line is constant. So the residuals, if you were to plot the residuals as a function of X or as a function of the predicted Y, their variability would look constant. Does that make sense? So your random component of mortality, for example, in that earlier example, the random component of it is constant for countries with low mortality and high mortality. And you can imagine that in something like that, it's an easy assumption to violate, in that countries with a low mortality, there might be lower variance than in countries with high mortality. But if that is violated, then probably another model is needed. The normality assumption here is dependent on X. So it's again, it's for a given X, Y are normally distributed. You can also think of that in terms of the residuals. The residuals are normally distributed. And a compact expression of all of this is contained just in this regression equation. So the linearity assumption is contained in this beta 1x. The homoscedasticity assumption is contained here, where we're assuming that the residuals are normally distributed with zero mean. So that means that the linear component contains all of the systematic variability, and the random variability is the same for all values of X. So the fact that the relationship is linear means that the mean of the residuals is 0 at all parts of the line, and the fact that they're homoscedastic means that they have a constant standard deviation. And as with all statistical tests that we cover in this course, we're making an assumption of independence between the observations. Any questions? Oh, getting close to the end here. So the Pearson's product moment correlation and the regression coefficient are very closely linked. There's a question online. I'll get to that in a moment. And they differ by a factor of the ratio of the two standard deviations. So this is how, if you remember, rho does not depend on which is X and which is Y, but the coefficient does. And this is how that change occurs. And if we were to scale both of the X and the Y so that they have a standard deviation equal to 1, then the coefficients and the Pearson correlation are exactly the same. Neat. Now, what's the question? When you have a data set and you want to run a regression analysis, you first have to make sure that the Y distribution is normal, or the model is assuming that. That is an assumption that you have to make, but it's an assumption that you can check after you do your regression. And if it is not met, you can choose a different model. So the typical thing to do with regressions is you do your regression and then you make some diagnostic plots to tell you whether your assumptions were met. And one of those plots would be a plot of the residuals to see how normally distributed they look. So with the inference test, you could think of the inference in terms of the correlation coefficient, as I wrote down earlier, or in terms of the regression coefficient. And those two hypothesis tests are equivalent due to the equivalency I showed on the previous page. If one is 0, the other is 0. So I had one example. This is from your textbook. I guess maybe we have a few minutes to go through it. I just wanted to give a sort of typical linear regression problem and talk through it with you. And show you an example of the output of a linear regression. So this is a data set of body measurements of weight in kilograms and height in centimeters of 507 individuals and plotted as a scatter plot. So we're using height as the X predictor variable and weight as the Y response variable. Doesn't really matter which way you do it. But let's just talk through these questions. Describe the relationship between height and weight. Can anyone describe it for me? It's positively associated. Yep. Write the equation of the regression line and interpret the slope and intercept in context. So this is the output of our regression. How would you use that to write the regression equation? Remember that was like y equals beta 0 plus beta 1x. What would it look like using the name, using say variable names weight and height?
So it's your intercept 1.0.
Intercept is minus 105. Can anyone say out loud in words what the regression equation would be?
Well, it's the intercept plus the slope times the value of x, but I'm trying to figure out slope.
Hard to read. So the slope is 1.01.
Why would we know that?
Yeah.
So this table, it has two rows, one for the intercept and one for the slope of the coefficient for height. So the second one is it's the coefficients for the variable of height, or it's the slope. So it's giving us the best estimate, so the slope for the best fit line, as well as a standard error on that estimate, the t-statistic that using that equation that I showed before, and then a p-value calculated from that t-statistic.
So it would be y hat equals negative 105.0113 plus 1.10176 times x.
Yep. Yep. And you could even go a step further and say that its weight is equal to minus, or you could say weight in kilograms is equal to minus 105 plus 1.0176 times height in centimeters.
Okay.
Because these estimates are unit dependent.
Okay.
So as long as height's in centimeters and weight's in kilograms, then weight equals minus 105 plus 1.0176 times height. Interpret the slope and intercept in context. So how about this intercept? What's that?
That's what you would theoretically weigh if your height was 0?
Yeah. So it's not a very interpretable thing. I mean, well, yeah, it's not. We could interpret it as sort of a correction factor. So in looking at a direct proportional relationship between weight and height, the weight would be 1.01 times the height minus this correction factor. But it's not very useful on its own. Nobody.
Say that it has no realistic like interpretation, or that's
As a correction factor?
no, I mean just feel like the intercept. So like in reality, that doesn't really have like.
In reality, it doesn't mean anything. Yeah, because nobody is 0 centimeters tall. So yeah, then the intercept. It's often the case that the intercept itself is not very useful for interpretation. It's just used for the predictions. Yep.
It wouldn't be for every centimeter.
For every centimeter taller.
Yeah, 1 kilogram would be.
Yep. Yeah, so the interpretation here is for every centimeter increase in height, on average, there's a 1 kilogram increase in weight. And that is the thing where usually we're interested in the intercept. So, or sorry, that we're interested in the inference on, if there's a relationship between height and weight. You will get a p-value for the intercept, but often we don't care about it.
What is the random error?
Yeah, so the random error is not included in a table of regression coefficients. However, you can do an ANOVA table for linear regression, and that will show you all of those components. It'll show you your sum of squares of errors, and it'll show you a sum of squares of your regression line for this regression. So let's see, C, do the data provide strong evidence that an increase in height is associated with an increase in weight? State the null and alternative hypothesis, report the p-value, and state your conclusion. If you had another exam, I would put something like that on it. So, yes, no? Does it provide strong evidence? Yeah, it does. P-value of 0 to 4 decimal places. The null and alternative hypotheses.
There's no correlation for it all. There is association.
Yep. Yep. P-value of less than 0.0001. Yeah, question?
Would there be like a confidence interval for correlation?
Yeah, well, so can you tell me how you would construct a confidence interval for the coefficient between height and weight?
Use the standard error.
Yep. Yep, just multiply this by 1.96 and plus or minus that, and that'll give you your 95% confidence interval. Good question. So let's see, what else? The correlation coefficient is 0.72, calculate R squared. That's pretty easy, right? 0.72 squared. And interpret it in context.
Oh, that's the slope, not.
Yeah, so how would,
1.0176 is the slope, it's not the
right.
correlation.
So you would have to multiply that by the, what was it, the standard deviation of x divided by you take the slope times standard deviation of x divided by standard deviation of y to turn it into a Pearson correlation. And how would we interpret R squared here?
Coefficient of determination.
Yeah. So 0.7 squared is going to be about 0.5. So if it were 0.5, what would you say based on that? No, give me a quantitative interpretation if R squared is 0.5.
Would it be kind of like 50% of our relationship is explained by the regression model?
Close, yeah. That would mean 50% of the variation in weights is associated with variation in height. So you can explain half of people's weight just on the basis of their height, and the rest is other things. If you were to add size of the waistline, that would help you explain more. If you were to add, you know, I don't know, the bone density or something like that, that would help you explain more. If you were to add whether or not they're wearing heavy shoes, then maybe that would explain more.
Can you state that one more time? 50% of the
50% of the variability in weight is explained by variability in height, or vice versa. 50% of the variability in height is explained by variability in weight.
I guess I'm just taking back to the question I asked earlier about attributing it to error.
Right.
Right, so like you're saying like what I intuit, you know, that it would be other factors, but like wouldn't you just have to say, since you didn't measure those things, that it's error?
Yeah, in terms of the data that we have here, that other 50% is error.
Okay.
Because we can't
Just think error is
predict it.
judgy or something.
Not to the
It's
statistician.
judgmental.
There's nothing judgmental about error.
Okay,
Unless it's not normally distributed, then it's bad.
okay.
No, this is not error like you did something wrong. This is just errors. It's error in your prediction of y.
Okay.
You make your best prediction of y, and you still have that amount of error left. And you can imagine that no matter how many body measurements you took of these individuals, you would still have some residual error. Okay, that's it. Oh yeah, reminder, please do fill out your evaluation forms. They're important for my getting tenure eventually. Hunter cares about them, so you need to fill them out and you need to say I'm okay.
you need to say.
Yeah.
It's always so difficult. Once you figure out that they actually do matter at some point in a professor's career, it's like you have to actually be careful how you word it, and you don't want to just say, oh, he's cool, he's cool.
Yeah.
We'll get your tenure.
Thanks, Leo. All right, I will see you all downstairs.